Bounded linear functionals, BDD. Bounded linear functionals. Bounded linear functionals on LP mu. LP mu. Linear functionals on LP mu. LP mu. LP mu. Concepts and definitions. Concepts. Concepts and definitions. Definitions. Concepts and definitions. Definition 1. Suppose L is a normal linear space. Let L is a normal linear space. N, L is normal linear space over K equal to set of real numbers or complex numbers. Set of real numbers or complex numbers. Set of real numbers and complex numbers. A linear function f on a linear function a linear function f on L f on L f on L is said to be bounded is said to be is said to be bounded is said to be bounded if there is a constant m is greater than 0. If there is a constant there is a constant m is greater than 0. Constant m is greater than 0 such that mod f of x is less than or equal to m. St means such that mod f of x mod f of x mod f of x less than or equal to m less than or equal to m into norm of x into norm of x to norm of x for all x belongs to L. For all x belongs to L. X belongs to L. The norm f the norm the norm f the norm f of linear functional f the linear functional linear functional f linear functional f is defined by norm of f is defined is defined norm of f equal to norm of f equal to infimum of m infimum of m in form of L such that from N such that mod f of x is less than or equal to mod f of x mod f of x is less than or equal to less than or equal to m norm of x m into norm of x m into norm of x for all x belongs to L all x belongs to L x belongs to L based upon this definition we'll prove one theorem 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 page number 72 page number 72 theorem page number 72 theorem. So question formation is prove that or show that P and Q, prove that or show that P and Q non-negative extended real numbers. P and Q, P and Q non-negative, 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 non-negative extended real numbers. Extended real numbers. Extended real numbers. Extended real numbers such that 1 by P plus 1 by Q equal to 1 for any G belongs to L of Q. L of Q. Define f of G. F of G. F of G. Define f of G. LP of mu. 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 Tends to K. Tends to K. Tends to K by FG of F. By FG of F. FG of F. FG of F equal to FG d mu. Integration X FG d mu for F belongs to LP of mu. LP of mu. LP of mu. LP of mu. Then two cases will arise. Case number 1. FG is bounded linear functional. FG is BDD is bounded linear functional. Linear functional. bounded linear functional, bounded linear functional, bounded linear function on LP of mu, on LP of mu, on LP of mu, B equal to, B equal to norm FG, norm FG equal to norm G of Q, norm G of, norm G of Q, norm G of Q. Proof. Most important for 10 marks question. Proof. Proof. Okay. Proof. Let F1, F2 belongs to LP means let F1 comma F2 belongs to F1 comma F2 belongs to LP mu, LP mu, LP mu, LP mu, and alpha comma beta belongs to K, and alpha comma beta belongs to K, belongs to K, alpha comma and by linear of integral, then by linear of integrals, integrals, linear of integrals, linear of integrals, we have, we have Fg alpha F1, Fg alpha F1 plus beta F2, beta F2, F2 equal to integration, integration x alpha F1 plus beta F2, beta F2, beta F2, G d mu, G d mu, d mu, G d mu. So here alpha is the constant. You have to take outside alpha integration x F1 F1 G d mu, G d mu plus beta is outside integration, integration x x F2 G mu, G d mu, d mu, d mu, that equal to alpha into f of g f1, f of g f1 plus beta, beta into f of g f2, f of g f2. Proving fg is linear functional. Proving fg is proving that fg, that fg, that fg is linear functional on, is linear functional on functional on, linear functional on LP mu, LP mu, LP mu. To to prove the boundedness, to prove the to prove the boundedness of boundedness, to prove the boundedness of FG, we consider the different cases of FG. We consider the different cases. We consider the different cases. Different Consider the different cases. Different cases. Consider the different cases. Case one. Here, case one. Case one. Case one. Suppose P equal to 1, so that let P equal to 1 and P equal to infinity, and P lies between 1 to infinity. Three cases. P equal to 1, so that Q equal to infinity, so that Q equal to infinity. Then G belongs to L infinity. G belongs to G belongs to L infinity mu. L infinity mu. G belongs to L infinity mu. G belongs to L infinity mu. G belongs to L infinity mu. L infinity mu. And for any F belongs to Ln, for any F belongs to L1 mu. L1 mu. L1 mu. We have F3 of F equal to, we have Fg of Fg of F equal to Fg of F equal to Fg mu. Fg mu. Fg mu by Holder's inequality. By Holder's previous chapter, by Holder's inequality. Holder's inequality. By Holder's inequality. By Holder's inequality. Modulus of F of G of F of G of F of G of integration. Modulus integration Fg d mu. Fg d mu. Fg d mu less than or equal to Fg d mu less than or equal to norm F1, norm G infinity, norm F1 into norm G infinity. infinity, that equal to norm f1, norm f1. So where m equal to where m equal to m equal to norm of g infinity, norm of g infinity. So that fg is bounded linear functional. So that fg is BDD means bounded linear functional, linear functional, bounded linear functional, bounded linear functional, bounded linear functional, linear functional, bounded linear functional. Case 2. Case 2. Suppose p equal to infinity, let p equal to infinity, p equal to infinity, so that q equal to 1, so that q equal to 1, q equal to 1. Then g belongs to L dash m, then g belongs to L dash mu, and for any f belongs to L infinity mu, f belongs to L infinity mu, L infinity mu. We have fg of f equal to, we have fg of f equal to integration xfg xfg fg d mu d mu. Again by Holder's inequality, again by Holder's inequality, Holder's inequality, by Holder's inequality. Now fg of f, fg of f, now fg of f, now fg of f, that equal to fg of f equal to and fg of f equal to integration x fg into fg d mu less than or equal to norm f g, norm f infinity into norm g of 1, that equal to m into norm f of g, norm f of infinity, norm f infinity, where m equal to norm of g 1 norm of G1, showing that Fg is bounded. This shows us, this shows us, this shows us Fg is bounded in this case. Fg is BDD, means bounded in this case. In this case. In this case. So case number 3. Case 3. Case 3. So the p-value lies between 1 to infinity. P-value lies between 1 to infinity. That means 1 less than p less than 1 less than p less than infinity. Infinity. Enter. Now G belongs to, now G belongs to LQ, LQ, enough mu. And for any, F belongs to, for any F belongs to LP, F belongs to LP of LP of LP of mu. We have Fg of F equal to, we have Fg of F equal to Fg of F equal to Fg of F equal to integration Fg d mu, integration x Fg d mu, right? By Holder's inequality, we get Holder's inequality. By Holder's inequality, we get Fg belongs to Fg belongs to Fg belongs to L dash mu, L dash mu, and norm Fg of 1, norm Fg of 1, norm Fg of 1 less than or equal to norm F P, norm G, norm G, norm G Q, which gives Fg of modulus of Fg of F, Fg of F, Fg of F, that equal to integration xfg d mu, that equal to norm Fg of 1 is less than or equal to norm Fp, norm Gq, norm of Fp, norm of P into norm of GQ, norm of GQ, norm of GQ. FG is bounded linear function. This showing that this showing that this showing that this showing that FG is bounded linear functional. FG is bounded linear functional linear functional bounded linear functional bounded linear functional with m equal to g of q, with m equal to norm g of q, norm gq q. So in all cases we find that norm f of g that equal to infimum of m, infimum of infimum of infimum of m, infimum of m such that fg of f is less than or equal to fg of f, fg of f, fg of f, fg of f, fg of f is less than or equal to m norm of f, norm of fp, norm of fp, norm of fp for all f belongs to f belongs to mu lp of mu, lp of mu, lp of mu, lp of mu in such that norm fg is less than or equal to norm fg norm fg is less than or equal to norm g of q, showing that fg is g of q. To prove that b is suffice to show that to prove sufficient it is enough to show that enough to show that is enough to show that enough to show that enough to show that there is f naught belongs to there is f naught belongs to lp of mu, lp of mu, lp of mu such that mod fg of f naught equal to, so norm f naught p, that means norm f naught, norm fg of naught, fg F naught, F naught, F naught, P, F naught P, and norm G of P, norm G of G of Q, G of Q. Suppose let G belongs to G belongs to G belongs to LQ mu, LQ mu. Given right, given that, given that, given that, write F naught equal to, write F naught equal to, write F naught equal to norm G, norm G, Q by P, Q divided by P. Q divided by P. This is the signum of G. SGN means signum of G. SGN. SGN means here signum of G. Where 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 sigma of F equal to SGN means signum function. Sigma of A equal to 1, comma 0, comma -1. This is signum function. SGN means signum function. 1, 0 or -1 according to according to according to A greater than 0, A greater than 0, A equal to 0, A less than 0, A less than 0. Three cases will arise. Then we have then we have then mod F P that equal mod G of mod G whole power P. Here this is the Q. So that so that so that integration modulus of f of x1 integration mod f naught whole power p d mu d mu that equal to integration integration x mod g whole power q d mu less than infinity showing f naught belongs to showing 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 F naught belongs to LP mu. F naught belongs to LP mu, showing LP mu. LP mu. And F naught P equal to norm GP, norm GQ, and now F naught P equal to norm G, norm G, norm G. Hmm? F naught that equal to integration on x F naught G d mu, F naught G d mu, F naught G d mu, that equal to integration x G into mod G q by P, 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 signum function of G d mu. SGM means signum function. SGN. SGN is SGN. Signum of G d mu. D is d mu. That equal to integration x G SGN GN equal to G mu q by P d mu q by P d mu, that equal to integration mod G whole power 1 plus q by P, 1 plus q by P, 1 plus q by P d mu, that equal to where mod G equal to G signum G. So integration x mod G whole power q, where since 1 plus q by P q equal to q, that equal to norm of F naught whole power P, that equal to F naught P into norm norm of f naught p power p minus 1, p power p minus 1, p minus 1, p minus 1, that equal to that equal to norm f naught p, norm f naught p into norm g of q, to norm g of q, since norm of f naught p minus 1, integration x, integration x mod f naught, mod f naught p d mu, d mu whole power p minus 1 by p minus 1 by p, that equal to integration x norm norm g, norm g whole power q for q d mu, d mu whole power 1 minus 1 by p, 1 by 1, nothing but divide by p, p minus 1 by p is nothing but 1 minus 1 by p, 1 by p, that equal to norm of, norm of g to q. Hence, for any g belongs to q, hence for any g belongs to lq mu, g belongs to lq mu, lq mu. There is f naught belongs to, there is f naught belongs to lp, lp mu, for which for which f of g, f of g, f naught, that equal to fp into norm g, norm g q, showing norm fg equal to norm fg equal to norm g, norm of g. In these three cases, hence we proved the result. Next. Most important theorem, Ries representation theorem. One more theorem we'll discuss today. That is Ries representation theorem. Ries representation theorem. Second theorem. Page number 74. theorem. Ridge representation theorem. Ridge representation theorem. Ridge representation theorem. Sometimes they will ask, state and prove ridge representation theorem. So statement, prove that or show that. Sometimes they will ask, prove that or show that. Question formation is like that, right? So suppose x comma, suppose x comma a is a measurable space, is measurable space, measurable space. X comma a is a measurable space. Mu is a finite measure on x. Mu is a finite measure on x. Finite measure on x. F is a bounded linear functional tau. This is nothing but tau. F is a bounded linear functional on F is a bounded linear functional on functional on bounded linear functional on is a bounded linear functional on LP mu. LP mu. LP mu. There exists a unique element G belongs to LQ mu. There exists a unique element. Unique element. Unique element. G belongs to LQ mu. LQ mu. LQ mu. Such that F of F F of F or tau of F that equal to integration x fg d mu fg d belongs to each f belongs to lp mu lp mu lp mu where p and q are such that where p and q are such that 1 by p plus 1 by q that equal to 1 that equal to 1 that equal to 1. Also norm f equal to norm gq. Also norm of f equal to norm g q. G q. Proof. Proof is most important for this. Proof. True. True. We first prove uniqueness of we first prove uniqueness of uniqueness of uniqueness of G belongs to LQ mu. G belongs to LQ mu. G belongs to LQ mu. Let G1, G2 be the functions. Let G2 be functions such that be FNS functions estimates such that FG of F, FG of F that equal to FG of F equal to FG1 d mu integration X FG1 d equal to integration X FG2 d mu d mu equation number 1. Equation number 1. One. Equation number 1. For every F belongs to for every F belongs to LP mu LP mu LP mu. Since x power p of x, since integration z of x it as j of x d mu j of x d mu that equal to mu of x mu of x mu of x less than infinity by hypothesis we have z of x belongs to LP of a z of x belongs to LP of mu LP mu so that one gives us so that so that so that equation number 1 gives us gives us gives us gives us integration x z of x g1 d mu d1 mu d1 mu j of x g1 mu g1 mu g1 d mu correct d mu d mu that equal to integration x j of x j of x g2 d mu g2 d mu. Mu g2 okay. So G1 equal to G2 in LP, proving the uniqueness of G. Hence, hence G1 equal to G2. G1 equal to G2 in LQ mu. LQ mu. LQ mu. LQ mu. LQ mu. LQ mu. Proving the uniqueness of G. This proving the this proving the uniqueness of G. Uniqueness. Uniqueness of G. Uniqueness of G. So now of F equal. So now F equal to 0. That implies F of F. F of F. F of F equal to 0. F of F equal to 0. F of F equal to F of F equal to 0. F of F equal to. Therefore, assume that Now p greater than 0, consider p is greater than 1, p equal to 1 separately. Then case 1. Case 1. Then case 1. P is greater than 0. Case 1 is p is greater than 0. P is greater than bounded linear functional using the bounded linear function. Bounded linear function. Bounded linear functional using the bounded linear functional. Linear functional. F defined on LPQ. F defined on LPQ. LP LP mu. LP lambda, lambda equal to f of xe. Lambda equal to f of xe. F of xe. F of xe. F of xe. Any e belongs to A. E belongs to A. So now we claim lambda is a signed measure on A. Where lambda is a signed measure. Signed measure. Signed measure on A. Script A. Script A. So E is absolutely continuous with respect to n. Yeah. Absolutely continuous. Absolutely continuous. Absolutely continuous with respect to mu. With respect to mu. With respect to mu. Lambda pi equal to 0 and xi of pi equal to 0 since xi of pi equal to 0. Xi of pi equal to 0. 0. Also, if here different sets in A, if A and B, different sets in A, then X A union B equal to A. Then X A union B equal to X A plus X B. So by linearity of F, we get lambda of A union B equal to lambda of U union B equal to lambda of A union B equal to pi of F of X A union B. X A union B, that equal to F of X A plus X B, A plus X B, that equal to F of X A plus plus f of xb of a plus xb. Lambda of b, lambda of b shows that lambda is this showing this shows that lambda is finitely additive finitely additive. Again e again e equal to again e equal to again e equal union I equal to 1 to infinity 1 to infinity 1 to infinity ei where 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 ei intersection j equal to null set ei intersection ej e intersection ej equal to null set for I is not equal to for I equal I is not equal to j and an equal to an equal to an equal to I equal to 1 to n ei union of I equal to 1 to n 1 to n ei we have we have we have model of we have xan xan minus xe xe norm norm p whole power p that equal to integration x x xan minus xe xe p equal to d mu that equal to integration x power p d minus an d mu that equal to mu of e minus an e minus an e minus an that equal to mu I equal to n plus 1 infinity infinity e power I e power I power I that equal to sigma I equal to 1 to n sigma I equal to 1 to infinity sigma n plus 1 to infinity mu of ei mu of ei mu of ei showing norm of xan XAN minus X F norm P tends to 0, as n tends to infinity, as n tends to infinity, as n tends to infinity. Since n equal to 1 to infinity, m of En equal to E, therefore, x of En tends to x of E, as n tends to infinity, as n tends to infinity, n tends to the space, in the space, LP of B, in the LP of, since F is continuous, since F is continuous, F is continuous. Since F is continuous, since F is continuous, so F is continuous. We have F of AXN. We have F of AXN, F of XAN, we XAN. My tends to F of XA, F of XA, F of XA. So on, so on. Rest of the theorem, do it as homework. Most important theorem for 10 marks question. Page number 76, 77, and 78. Page number 76, 77, and 78. Do it as homework. Thank you. Thank you very much. I'm leaving.